So now let's look at greenhouse gases and how they're defined. So first off, we have potency. Now, what makes a greenhouse gas effective at absorbing IR radiation? We have to consider a few things. In the atmosphere, what is its concentration? How long does it stay in the atmosphere is also important. And lastly, its radiative forcing. So this is a measure of how well it absorbs the radiation. And so this is influenced by the number of vibrational modes and also the frequency or the energy of the wavelengths that are absorbed. So there's two ways in which we can quantify potency. So the first is what they call the relative instantaneous radiative forcing. So it's defined as the effect of an incremental addition of gas has on IR radiation. And so we'll look at a table of these values. Again, it's just a numerical value to kind of relate the different gases. The one that's more commonly used is the global warming potential. So this is a ratio of greenhouse gases and warming from 1 unit of greenhouse gas per 1 unit of CO2. So they make a ratio giving CO2 a unit of 1 and relating the other greenhouse gas to CO2. And it's usually in units on the scale of 100 years. So these are some values for GWP for different gases. And so we see that some of these gases are much more effective at absorbing IR radiation, such as refrigerants, CFCs. But if you consider the concentration of CO2, it is the most important of the greenhouse gases. These CFCs have such a high potential for global warming, mainly due to their lifetime in the atmosphere. They have a very, very long lifetime. Here we have a table of different greenhouse gases, and it shows the relative instantaneous radiative forcing and global warming potential for these gases. And so we have relative values where CO2 is given a value of 1, and all the other gases are relative to CO2. And so we see that methane is about 21 times better at being a greenhouse gas or contributing to warming than CO2. And then when you get to these refrigerants, these CFCs, we see that they're thousands of times more of a global warming potential than CO2. Now, these differences aren't actually seen in the percent total radiative forcing because of such low concentrations of the other gases. What we see is that CO2, at least in the 1990, with a concentration of 354 ppm, it was responsible for 61% of the absorption of IR on Earth in the atmosphere. And then we see that methane is the second highest at 17, which is quite a large contribution. The last thing I want to note about this is the lifetimes here are different than what I would expect. Just looking at the CO2 lifetime that's been calculated, I'm unsure how they've calculated these lifetimes. They are different, I guess, a different definition of lifetime than what we did when we were looking at the carbon cycle and we used the box model to determine the residence time. This is not the mean residence time. It is a different calculation for lifetime. So review this table. There's a lot of information on here and kind of puts in perspective how much each of these gases contribute to global warming. So let's look at how some of these greenhouse gases have increased over the last 250 years. We see in all cases exponential increases in all of these gases. I will say these refrigerants have leveled off somewhat because of the Montreal Protocol. They were banned due to their destruction of the ozone layer. And we also see that these gases, methane and CO2, their concentration does correlate with changes in local temperature. Now, the climate change deniers like this figure. They use this figure as a way of saying that CO2 and methane, greenhouse gases, do not increase the temperature. Because what you notice in this figure, so we're looking at thousands of years, hundreds of thousands of years, and we're looking at CO2 level, we're looking at the methane levels. If you notice in these figures, the CO2 concentration is always lagging behind the temperature a little bit in a lot of ways. It's always a little bit lagging. Seems like the temperature is going up first, then the CO2 is released. And so their argument is that it's actually temperature increases CO2, not CO2 increases temperature. Well, it's both, correct? What caused the temperature to increase initially was an increase in CO2, but then upon a higher temperature, you then continue to release CO2 through, say, soil or other positive feedbacks that occur with increased temperature. So I just wanted to let you know that there are these kind of arguments that keep coming up that I hear less and less through climate change deniers, but that is definitely one that is commonly repeated. And so the next few slides, I'm just going to go through them. There is lots of ways to kind of, in some ways, manipulate or show your best face when showing temperature data over time or even CO2 concentrations over time. This is a very common figure that you'll see in textbooks. They call it the hockey stick. It goes back 1,000 years. And again, it has kind of selected a very nice window for people that are pro climate change to illustrate that CO2 is going up. And so we do see this very flat line at 280 until we get to the Industrial Revolution, and then we see an increase that's exponential and can correlate with our exponential use of fossil fuels. We see the jaggedness of the annual pattern of CO2 given the spring and the fall cycles of CO2 being released in the fall, and in the spring and summer, CO2 being taken up by the biota. So again, we have temperature change over different periods of time. So here we're at a scale of about 1 million years. We're on a scale here of 10,000 years, and here we have 1,000 years. So when we look at this, we see all of these major ice ages over the last million years, but we also see times when the Earth was much warmer than what it is now. Again, climate change deniers use these sorts of figures to minimize what is occurring in the present day. They also like to point out, even in recent times, higher temperatures, such as the Holocene maximum after the last ice age, and also even the medieval warming period where they were growing grapes in the British Isles. And so temperature does change over these periods. And again, we were looking at the CO2 concentration at this same period, and it looked much more like this. So there's a lot going on with temperature and climate. Last, let's just look at this figure. This one goes back 500 million years, and we definitely see that the Earth was warmer at one time. There was life on Earth under these conditions. So to finish this video, let's look at some factors that change climate and also different scenarios that can be additive or take away from these changes through positive and negative feedbacks. And so in terms of factors affecting climate change, well, a change in albedo will change how much solar radiation can actually be absorbed in the Earth's atmosphere. We also have some cyclic things such as El Nino, which happens every 5 to 10 or sometimes 15 years, where the ocean currents change, which then changes the directions of winds within the atmosphere. Remember, ocean circulation and atmospheric circulation are coupled, and in doing so, they can change the climate on Earth. Sunspot cycle, it's about an 11-year cycle, but again, there's other variations such that the solar radiation coming from the sun, the intensity changes over time, which will affect the temperature in the atmosphere. There are long-term changes in the rotation and tilt of the Earth, which definitely affects climate. This Milankovitch theory is a primary factor that leads to ice ages and warming periods over the time scale of 100,000 of years. Another one is air pollution. This is sometimes more on a local level, but the introduction of particulates and aerosols to the atmosphere affect climate for sure, as does volcanic activity for the same reasons. So to end this video, let's look at some positive and negative feedback. So if we were to increase the temperature of the Earth due to an increase in CO2 or other greenhouse gases, how will that affect the Earth system? And so as we go through these, I want you to think about how you would logically go through and add more scenarios to this list. And so first, increase in temperature would increase the amount of water vapor. You would get a little more water to be in the gas phase at a higher temperature. That would increase the temperature more. Therefore, we get a positive feedback. But a higher temperature would lead to more cloud cover, more water condensed in the atmosphere. And that would lead to higher temperature if the clouds were at high altitudes. Clouds at high altitude seem to trap heat better. But if you get a cloud cover that's at a lower altitude, you'll actually lower the temperature of the Earth because you get more albedo. So we get a negative feedback there. Snow cover will go down if the temperature increases, and therefore that would lead to more temperature increase because we have less albedo in this scenario. An increased temperature will increase the temperature of the soil, which will release methane and CO2. There's a lot of frozen soil in the Arctic, and as that thaws, bacteria would then start decomposing the organic matter, which would release the CO2 and the methane. So positive feedback there as well. So to finish this topic, let's consider if the atmosphere temperature increased, the temperature of the ocean would increase, which would release potentially methane hydrates, which are locked away at the bottom of the oceans or in the continental shelves of, say, the Arctic Ocean, such as Siberia. If this methane was released, it would be a positive feedback, given that methane is 21 times more potent a greenhouse gas than CO2. And many scientists are concerned about this scenario and that it could lead to a runaway greenhouse effect. If the temperature of the atmosphere increased, we'd also form more deserts, but that would increase the Earth's albedo and be a negative feedback. The temperature of the ocean increased. There's a potential for the Great Conveyor Belt to be slowed or completely shut down. Scientists believe that if this occurred, it could potentially produce another ice age. And so measurements have shown that this is actually occurring, that the thermohaline circulation is slowing down, and therefore this is something that we should be concerned about. Lastly, a few more things. Increase in soot or black carbon. That can either have a positive or negative feedback. It has a positive feedback in that the black particles absorb the radiation, and also if the particles get on, say, a glacier or snow cover, you can imagine that they would increase melting of that reflective surface. They have a negative feedback in all these particles can actually scatter light and prevent sunlight from getting to the Earth's surface. Pollution regulation on sulfur or particulates. Well, what to consider here is that sulfur causes the formation of aerosols, and these types of particulates and aerosols end up cooling the Earth, and so they are a negative feedback to global warming. So in terms of pollution regulation, well, maybe negative feedback in terms of pollution regulation isn't the way to approach it. There'd be a positive feedback if you regulated these pollutants, but essentially these pollutants have a negative feedback on climate. But if you started to regulate it such that you lower the amounts of these constituents in the atmosphere, that would be a positive feedback. Very quickly, volcanic activity, nuclear winter, these are definite possibilities. These have negative feedback on climate. Last thing I came up with was if you had an increase in CO2, you'd increase the temperature and you'd increase plants and biological storage of CO2. So that would be a negative feedback. So to end this video, we need to consider many things in terms of modeling the climate, and it's not just CO2 levels. It has to do with other greenhouse gases and aerosols, as I just discussed. The particulates and sulfur containing aerosols play a huge role in climate. And so what we have here is looking at a model right here of what the temperature should be in terms of change if you just considered CO2. What we have in the jagged is what we have observed. So if we just consider CO2, it's not modeling the actual observed change in temperature. But once we consider a lot of factors like greenhouse gases and aerosols and solar irradiance, well, once we do that, what we find is that it actually does follow the observed trend pretty well. So you might want to look at this figure without all these lines on there. But nonetheless, this is where we're going to leave this topic. You all will continue talking about this when you give your presentations. So this is just an introduction to climate change. You guys will let everyone know the specifics as you give your talks on different topics.